This comes out of section 8.4, derivatives of log functions. So it's a very straightforward max-min question. Just says find the max-min, if there are any, of f of x equals ln x over x. So hopefully your first thought would be I need to take the derivative of that. And so I'm going to use quotient rule to say the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. Little straightforward simplification of that says that this is 1 minus ln x over x squared. So there are some interesting values here. It turns out that x can't be 0. You look at the original equation there and you have 0. X is a denominator, so clearly x can't be 0. Also, you've got natural log of x, which means you can't natural log 0 or anything negative anyway. But so if I look at what critical values do I have, x equals 0 I suppose is one of them, but the more important one that I'm really going to look at is what makes 1 minus ln x equal to 0. And that is if 1 equals ln x, which means, and remember that this is log base e of x, so e to the 1 equals x. So what we really want to look at here, in terms of our number line, sure 0, we'll put it there, but e, and see what makes, whether the derivative is positive or negative will determine whether this thing is increasing or decreasing. So if I put in a number smaller than e, like 1 for example, I can have 1 minus the natural log of 1, which is 0, over 1 squared, and this shows up as being positive. It's increasing up to there. If I put in a number greater than e, like 1,000,000, this numerator will be negative in the derivative, and I'll definitely have decreases. So I increase, then I decrease. So I definitely have a max. In fact, I have an absolute max at e comma something. Now to figure out what that something is, I just put e into the original function, and if I say ln e over e, that point is actually 1 over e, because ln e is just 1. So this would be the answer, and on your graph that would be the highest ever that this graph ever goes. Now the second example I want to do is a curve sketching example. I want to do the curve sketch for the natural log y equals a natural log of x squared minus 1. So we would want to do all the usual, the domain, the intercepts, the symmetry, etc. So I'll do a little bit of that on pause so that this video doesn't end up 15 minutes long. First thing is the domain. What's inside that log needs to be positive, so I just solved that as a little inequality and figured out that the only numbers that wouldn't be in the domain are from -1 to +1. Anything smaller than -1 is fine, because when you square it and subtract 1 you'll be positive. Anything greater than 1 is fine as well. As for intercepts, if you try letting x equals 0, we already know that's not in the domain, so there's no y-intercept. For x-intercepts, I let y equals 0, I solve a little equation, and I figure out that at plus or minus √2, I have some zeros. So as soon as I have points, I like to put those on my graph, so I've got positive √2, comma 0, and negative √2, comma 0. And also, while I'm thinking about it, the symmetry, if I look at this thing, because the only x in the whole equation is squared, it does have even symmetry, so I'll notice that anything on the right side is going to look the same as on the left side. Now let's talk about asymptotes. I do some quick limits. First of all, I look at end behavior. If I put in gigantic positive or negative numbers for x, this thing just heads up to the sky, so I know that I don't have horizontal asymptotes. Now for vertical asymptotes, I can look at what's happening as I approach 1 from the right or -1 from the left, and I do have asymptotes there at x equals 1 and at x equals -1, that this graph heads towards negative infinity, so it's going down beside these asymptotes, and we'll have to now take a look at our derivatives to see what happens other than that. First derivative, relatively easy to take. You get y prime equals 2x over x squared minus 1. Critical numbers being 0, 1, and -1, but 0 is not even in our domain, so we don't really need to look in between there. And if you look to the left of -1, you'll be decreasing. To the right of +1, you'll be increasing. So second derivative takes a bit more work. You have to do the quotient rule, but if you do it carefully, you end up with something that you realize you've got -2 times something that's always positive divided by something that's always positive. So it turns out that this second derivative will always be negative everywhere in our domain, so it means we're concave down everywhere. So if we see if we can fit that all together, we don't have any max min points, we don't have any points of inflection, but we have these two vertical asymptotes and these two zeros. You have a graph that looks, something like this. So it's concave down, but it is heading off to infinity, and it's symmetrical, so it makes sense that it looks like this. It's still concave down, but on the left side was decreasing, on the right side is now increasing. So kind of a strange graph, but now that we know how to take derivatives of log functions, we can be asked to do just the same stuff we've ever been asked before in terms of curve sketching questions.